All right, today we're going to move into chapter 1, which is we're going to start talking in 1.1 on functions. And so first I figure out what a function is. So a function is a type of relation, and a relation is basically any relationship between two quantities. Now a function specifically is a special type of relation, and in this particular class we primarily deal with functions exclusively. We do once in a while we delve into something that's a relationship, that's just a relation, but mostly we deal in functions. And that is because a function is a very nice type of relationship that relates exactly one element from the domain into exactly one element in the range. So basically it takes one element from A and relates it to exactly one element in B. Now we call these, for instance, set A is the value, is what we're going to input, is what we call it. And here's set B, which is our output. Okay. So our input is from A and our output is from B. And so we also call the input the domain. So these are elements in the domain and these are elements in the range. Okay? So a function takes an input value, some element in this domain here, and it matches it up with exactly one element from over here. Okay? So it can't match up with two different ones over here, but it takes every element in this box, in the input box, or what we call the domain, and it matches it up with one element in the B, the output box, the range. Okay? So for instance, let's look at an example. So in our input, I'm going to put times. Okay, so we're going to use time as our input. So let me say 1, 2, 3, 4, 5, 6. Okay, so let's say we're doing an experiment and we're going to check at 1, 2, 3, 4, and 5 the temperature in an experiment. So I'm just going to put some different temperatures in here. Let's say 61, 62, 66, 68, 75, 81. Okay. So I have these different elements of time and I'm going to match them up with elements of temperature. So when you're doing an experiment, right, so at 1 o'clock we go in there, I'm going to check my temperature, and let's say our temperature was 61 degrees. So that matches up with 61. Okay, so we go in a little bit later and at 2 o'clock and we check again and the temperature is still 61 degrees. That's okay because it's okay for different elements in the domain to match up with the same element in the range. We just aren't allowed to have an element in the domain matching up with more than one, right? It wouldn't make sense for me to go in and at 1 o'clock find that the temperature was both 61 and 81 degrees. So think of it in that standpoint. All right, so let's see, what else? Also, okay, so if I fill out the rest of these, so if I go 3 o'clock, we'll say it's 66. At 4 o'clock, it was 75. And at 5 o'clock, it was still 75. And then we'll say at 6 o'clock, it was 81. So you may notice that I have a couple of temperatures over here, 62 and 68, which weren't used. That's okay. Okay, so it's all right if elements in the range aren't used, but every element in the domain must be matched up with something in the range. So let's just write out these different things here. So we have characteristics of a function. Okay, so first, every element, every domain, element in the domain must match with an element in the range. Okay, so that's the first thing. Everything in here has to be used and matched up. Okay. Some elements of the range, which is B, may not be used. Okay, so that's okay. Like we had the 62 and the 68 over here. They didn't match up exactly, but that's okay to have extra ones in there. It's just we can't have any domain that's not matched up with something. Right? So you may have noticed also that 1 and 2 both matched up to 61, and then we also had maybe 4 and 5 that were matched up to 75. So it's okay if elements in the domain match up with the same elements in the range. It's okay for elements in the domain to match same element in the range. That is perfectly acceptable. All right, and then the last thing that we're going to talk about is that makes something that we know that it's a function is that one element in the domain cannot match with more than one element in the range. So in our example up above with time, we never had, like, again, I said if I went in to check the temperature at 1 o'clock, right, the temperature can't be both 61 and 81. So every element in the domain only has one matching element in the range. So one element in domain matches exactly one element in the range. Right, so those are how we define a function, basically. So we have every element in the domain has to match up with something in the range, and then some elements in the range, it's okay if they're not used. It's okay for elements in the domain to match the same element in the range, right? They can all be the same, in fact. And one element in the domain can only match with exactly one element in the range. Okay. So, all right. So let's look at ways to represent a function. All right. So first of all, one way to do it is verbally. Right? We can talk about things like what we just talked about, the time and the temperature. We can think of it in terms of sentences. Okay? So for instance, an example of that, is a professional sports team and a function of a city. Okay, so when I'm thinking of terms of words, so to sort this out a little bit, when you hear that function of a city, that is an indication that they want the city to be the input. And the sports team is the output. Okay, so let's think about this a second. So let's choose a city. So since we're in Ohio, we'll choose Cleveland. Okay. Is Cleveland a function of its sports team? So we'll just say professional sports teams. So let's see, there's all the Cleveland Indians, right? They're currently playing baseball. There's the Cleveland Browns, and there's also the beloved Cleveland Cavaliers. Okay, so for Cleveland, right, there's the Cleveland Browns and Cleveland Indians and Cleveland Cavaliers as sports teams. So this is an indication that I have this one input and it's matching up with three distinct outputs. That goes against our rules for functions. So for instance, if I turned it around, if I had the Indians, the Browns, and the Cavaliers as inputs, if I said it in words, I would have said, is the city a function of the professional sports team? Then in this particular case, I could say yes, because the Indians, right, are a Cleveland team. There's no other Indians as far as I I know as far as professional sports teams. There's no other Browns, right? And there's no other Cavaliers. So they all match up with Cleveland. It's okay for my different elements in the domain to match up with same element in the range, right? If I could add like the Tigers here, and then that would match up with Detroit, right? Also, if I could put the Red Wings here, and that could also match up with Detroit, right? The same element. This is still a function because each one of these, there's no other Tigers. There's not a Tiger sports team that matches up with Phoenix or some other team. So this, in this direction, it's a function, but not in this direction. So the key is function of A. What comes after that, this is what we consider the input. Okay? So that's one way to tell what is being asked. All right. So we can also represent functions numerically. Okay, so that means that we can either list them as a bunch of ordered pairs, like I have 1 and 3, 2 and 5, 6 and -2. So this is another way to represent a function, and a quick way to tell. I could also put it in a table form just for, I have this function in x and y, so it's x comma y, so I could also write it as 1, 3, 2, 5, 6, -2. It's the same information, just organized slightly different. This is a way to represent it numerically. If I just was giving these 3 ordered pairs, I can tell that this is a function as well, because what I'm looking for, the key here, is that every element in the domain, which x is the domain, so these are my domain, only match up with one value of y in the range. And they do, right? So I have 1 matching up with 3, 2 matching up with 5, and 6 matching up with -2. If I happen to throw in here, what if I put in 1, -1, and I tack this on at the end here? Well, now I don't have a function anymore because now I have 1 matching up with 3 and 1 matching up with -1 as well. And so if I add this, then that makes it not a function. Okay? So another way to tell if something is a function is graphically. We haven't done a lot of graphing in here, but I hope that you remember that we could look at a graph, x, y, here in the plane. So let me just take and graph these 3 ordered pairs that I have listed up here to begin with. So 1, 3 says I'm going 1 in the positive x direction and 3 up here. Oops, so my point goes here at 1, 3. Then I'm going to move over here to 2, and then so 5 would be up here. I'm just plotting these as ordered, it's just an ordered pair. And then 4, 3, 4, 5, 6, I'll extend my out here, and -2 is down here. So, I'm sorry, this is just a dash. So I have these 3 points. I have, let me just call them A, B, and C. Now one way that I can quickly, I graph this, one way that I can quickly tell if something is a function or not is to basically look at vertical. I'm thinking in terms of vertical lines. So if something were to have the same x value and it matched up to more than one y value, then what would end up happening is as I would have 2 points on the same sort of invisible vertical line. So this particular function, right, this is a function, but when I add in this 4th point, this 1, -1, then I end up with this point right here, which I'll call D. And now B and D are on the same vertical line. So when I have an x value matching up with more than one y, right, then I get this sort of problem where when I draw in a vertical line, then it's going to hit it in more than one place. This is what we call the vertical line test. So if something is a function and I look at the graph of it, then it won't hit the graph in more than one place. So for instance, the x equals y squared is a graph that sort of looks like, it looks like your normal x squared, except for it's sitting on its side. So this is just, so this is x and this is y. Let's say that this is 1, 2, 3. Okay, so if I look at this particular graph here, this is the graph of x equals y squared, just kind of drawn hastily. This is not an example of a function because if I draw a line right here, right, let's say that this is, then I'm hitting in two different points, right? So in fact, if I think about this, if I plug in 9 for x, right, that could match up with 3 because 3 squared is equal to 9, so I have this ordered pair. And also, if I plug in 9, I could also get out negative 3. So that's like these. So if this is the point 9, oh, that's a terrible, but it would hit in two different places. This is just an example of what it would look like. 9, 3 would be way out here, and it would hit here and here. But it would hit in two different places. And so this is an example of something that's not a function. Okay, and then the last way that we can represent functions is with an equation. We say analytically. That's number 4. Okay, so it's as an equation in two variables. So for instance, y equals x squared plus 4x minus 6, or y equals 2x plus 1. These are both examples of a function. So if we're given an equation in x and y, there's ways that we can try and see if we know it's a function or not, because not every equation in x and y is in fact a function. So usually the easiest way to determine if something is a function is to solve for y. And this is to determine if something is a function. So in the two examples that I wrote up here, these are in fact functions of x. We say y is a function of x. Okay? These are in fact functions of x, and I can tell because y is by itself, and I just get y equals 2x plus 1, or y equals x squared plus 4x minus 6. Okay? When I solve for y, if it was going to give me two different values, let's use my example of x equals y squared. So for instance, right, it says the standard thing that I use, it tells me very quickly if something is a function, is I solve for y. And so I have y squared here. So what I'm going to do is I'm going to take the square root of both sides, and whenever I do that, I put plus and minus. So by turning this around, I'm going to just write y is equal to plus and minus the square root of x. So that means that I'm going to match up with two different values here. And so this one would be not a function. Right? This is what's going to happen when you try to solve for y if something isn't a function. So this is usually the quickest and easiest way to go about it. So let's just look at another example here. I have y minus x squared is equal to 3. So by solving for y, I just add x squared to both sides. When I do that, I get y equals 3 plus x squared. I don't get any sort of plus and minus situation, so this is in fact a function. All right. Once we know that something is a function, so now we know that this is a function and also these two beginning ones are also functions, one way so that we're not always wondering, wait, is that a function? Do I have to think about it? Once we know something is a function, we use what's called functional notation. And so basically what we do is we replace y with f of x. Now f of x is common, but we can use g of x or h of x or m of x, but we use this of x notation. And it's said y equals f of x. That's basically how we say it. It means that y is a function of x. And we use that in place of y because then that tells us quickly, yes, this is a function, you don't have to think about it. So in this particular case, since I know that this is a function, I could replace y with f of x and call this f of x equals x squared. Okay? So the way that we usually write this, we use this notation in a variety of ways. One, it tells us, it's a function. So f of x, right, we kind of say that this is the y value. So we usually write our ordered pairs as xy. They could also be written as x f of x, right? Because y and f of x are interchangeable. It's just the notation that I'm using. So also, this is a nice thing because we like to have shortcuts. So if I was using y equals 3 plus x squared and I wanted to say, I could say evaluate this at x equals 1. Okay, so then that would mean that I would plug in y equals 3 plus 1 squared and I get 4. Okay, so y is equal to 4 in that case. So a shortcut, the reason why we like this functional notation of instead of saying evaluate at x equals 1, we just say what's f of 1? And since we plugged in 1 and get out 4, we can say that f of 1 is equal to 4. So this is just some notation that we use when we know that something is a function, and it gives us a kind of a shorthand way of saying, okay, well then what's f of this? So let's look at what is f of 0 in our case. Well, f of 0 is an indicator that I need to put in 0 for x. So this is my x value. So f of 0 is the y coordinate that goes with it. So I plug in 0, and I can see that f of 0 is equal to 3. Right? As an ordered pair, I could also write this as 0, comma 3. Same here, up with 1, comma 4. Okay? So this is just another way that we use functional notation. Also, we like functional notation. Let's look at a different. So back here, we also had this y equals x squared plus 4x minus 6. So instead of y in that case, let me call that g of x, because I know that this is a function, so I'm allowed to use functional notation. So why we do this is because if I was dealing with f of x is equal to 3 plus x squared and g of x, and I was doing a lot of different calculations with them, it gives me kind of a shorthand to say that, oh, I'm looking at g, or oh, I'm looking at f. So f and g are sort of like their names, right? So just like, that's why we don't use descriptions for each other, like the girl in the curly hair over there, right? She has a name, maybe her name is Sheila. And so it's just like that with functions. So g it's the name of the function, f is the name of this function, and it's a way to distinguish them from each other without saying, oh yeah, we're using the x squared plus 4x minus 6. Okay? All right, so let's just look at, so let's take our two functions here and let's just evaluate them. Okay, so let's find out what g of 2 is. Right. So g of 2 is an indication that I'm using g, so I'm going to come over here, and 2 means I'm going to use this value for x when I plug in the value. So g of 2 is equal to 2 squared plus 4 times 2 minus 6. So g of 2 is equal to 4 plus 8 minus 6. All right, so combining my, let's see, I really have then just plain 6, right? Because I have 12 minus 6, which is 6. So g of 2 is 6. All right, so let's look at f of negative 2. So f of negative 2 is an indicator that I'm using f instead of g, and I'm going to plug in negative 2 for x. So that gives me 3 plus negative 2 quantity squared, which is really 3 plus 4. So f of negative 2 is equal to 7. Right? I could write both of these solutions as ordered pairs as well. Okay? All right, so let's look at a little bit slightly different one. Okay, so this time let's look at f of x plus 1. Right? So now this is a little bit different than the ones we've done before, but it still means the same thing. So in these particular cases up here, g of 2 and f of negative 2, I took the 2 and I plugged it in for x. So that is exactly what we're going to do here. So this is like my new x. So I'm going to take f, and I'm going to, everywhere there's an x in my f, I'm going to plug in this x plus 1. So f of x plus 1 is equal to 3 plus x plus 1 quantity squared. This was 3 plus x squared. X plus 1 is my new x, and so this is my equation. Now I can simplify this a little bit. I can say that this is 3 plus x plus 1 quantity squared is really x plus 1 times x plus 1, And when I multiply this out by itself, I get x squared plus 2x plus 1 when I combine my two middle terms. So I'm going to attach that over here. And now I have the 3 and the 1 are like terms, so in its most simplified form I can write x squared plus 2x plus 4. And that is my f of x plus 1. Right, so this ends our discussion on functions for the day.